In the course of trying to help explain to engineers what the next generation and the next generation after that, Gen 5 and Gen 6 of HVAC systems for the 2050 decarbonized grid will look like, we've created this graphic. It's a bit complex. So in this brief presentation, we're going to build this graphic and help you understand what it is, why it is. So we used to call it 5 kinds of HVAC. Now we think it really should be more closely called cost-effective HVAC decarbonization for the 2050 grid. So this is a byproduct of work we've been doing with the MIT D-Lab, and a course taught by Susan Murcott and working with her students. And this course, we gave a presentation in May on HVAC design for the clean energy grid. And this is an extract from that presentation. I'll show you a link to it if you want to go see it. Tell you who we are. We're a combination of things. I'm a computer engineer by training. Career A. Career B is in HVAC and in developing products in this field and in being an expert in the geothermal heat pump field. And we just do a lot of stuff, and I'm on the Binational Standards Committee. So I know a lot about this stuff and can try to help convey this information. And in that longer presentation at MIT, we resolved these questions. Will it cost too much to decarbonize? And you go listen to that. No, it won't. Definitely not. And a lot of people say we don't have the technology to decarbonize. And for buildings, that is bogus. It's just not true. There are a few things like Bunsen burners and all, but I think we showed that people have solved some of those too. I don't know what else there is on a big college campus, but I think in general, we have all the technology. And then there's the question about how much power is needed to do this. And there's no question some more power will be needed, but it's not going to be some dramatic amount. And the thing is, we can't prove that yet because we really need some better modeling and whatnot to be able to pull it off. So we're developing that now. And you can see this whole presentation at that link at the bottom of the screen if you'd like, including a piece before ours where the students explain the modeling technique. Just so you know what geothermal is, everybody knows, on a very hot day when it's hot outside, you got to use that 90-degree air to try to cool your house. And when it's cold outside, you got to try to use that 25-degree air to cool your house with an air source heat pump. Well, geothermal uses the ground. And the ground is a very stable temperature that vacillates a little bit around your average air temperature where you are. So your average air temperature determines that ground temperature. And it all uses just basic equipment like that. Looks like a furnace box, like any other furnace box. Nothing magical. Here's an example to show you how this field is advanced. This is a middle school done a decade and something ago in Texas. Beautiful school. This engineer set out, after 100-something geothermal systems installed, he set out to figure out how to do a net zero energy system. And so he gives some advancements, and I cover that more in the longer course, so go back and look at it there. But basically, it's all the same box, just the horizontal mode of the box up in ceilings. And this is what the economics model for that installation worked out. He figured out, see, these two bottom lines are the conventional line for what they call 4-pipe, chilled water, hot water, the geothermal curve for economics, and he figured out how to do them in Dallas for basically the same money. So that's not true everywhere, but it's kind of true right now with the IRA tax credits everywhere in the US. Now that makes a bunch of money. So that would save you $2 million over the course of 20 years anyway. And apparently this system's worked a little better than they even thought. Add solar at the time, $2.7 million for those rooftop systems you saw. And that saves you over time $9 million in 20 years. And that's not even the full life of the system. It's already effectively free. It already turns a profit in 20 years. And it's not even the full life cycle cost, which is even better because the ground loop in geothermal is going to last over 100 years. That's the official life. Nobody knows how much longer it will last, but it's some long time. Here's a study done by Department of Energy under the NREL, Renewable Energy Lab. There's that school in Texas, just outside Dallas, and you can see it actually produces more energy than it consumes over the year. So let's start building this graph. Now, these are all the heat pumps we're going to be talking about, all the way from air source heat pumps over here to geothermal heat pumps over there, and especially geothermal and these cold climate heat pumps, the things in between that are the high end right now of air source heat pumps. A lot of people know them under the title mini splits, for example. They're just a high end air source heat pump. In this graphic, you start to see first off that the fossil on the right there is just not a carbon solution. It's never going to be a carbon solution. It's never going to be decarbonized. And an infinite time to decarbonize. This curve shows the installation costs in general, although right now the installation cost for the IRA tax credits is not really more for the geothermal. It's actually the same as air source heat pumps, maybe even better. And so that's the installation cost. And you can see it generally goes up to the more advanced systems on the left. And then there's the operational cost, which you get it, you pay more in your system. It's got the earth as the anchor. It costs less to run the geothermal than it does the air source. So let's give them another little couple dots on the graph on the development here. This is the Engineers Association, ASHRAE, Mechanical Engineers Association. They decided to take one floor and make it geothermal and one floor and make it air source heat pumps to sort of settle the argument that was going on, which one's better. And this is the actual data that they took off this, as Xiaobing Liu and Professor Spittler at Oklahoma State and at Oak Ridge National Labs did this data, and they recorded a lot of excellent data. Now, I happen to know this, so this is the curve of the ground loop in blue, and the red is the air temperatures. You can see it's got an annual cycle. Now, I happen to know that the average air temperature in Atlanta is more like 54 degrees. So that loop is running a little hot. It should be running down here. That would be better. That would produce a more efficient solution. So this wasn't quite engineered to the perfect stage of what we do now in this field. And so this, how you tune these loops, this is what's taught. There's a specific training called the Certified Geo-Exchange Designer, CGD, of which I am, and maybe, I don't know, 1,000, 1,500 people. Your engineers, they took this training, would know a whole lot more than they do now, that's for sure. And so that's where it should be running. And there's ways that you do this. You tune it by wasting heat out of the system in the spring when it's very cool in the evenings and the power is very cheap. So there's specific ways you do this that are known by the people in the field, not known by others. You put in maybe ice melt loops under your sidewalks and under your parking lot areas and stuff. And you just use those in the spring to waste energy, or when there's snow and ice. It's an annual cycle thermal battery. That's the key point. This thing varies annually with its load. This big chunk of earth under a building. So let's pull that together here. And instead of thinking about these as heat pumps, let's now think about what the thermal battery is involved here. So for example, in the air source heat pumps, you have no thermal battery, and in the ground source heat pump, you have an annual thermal battery. So that's a spectrum of end to end on what the limits are here, using the earth and using nothing. So again, Inflation Reduction Act, price, the installation cost is actually level. So this is some data, the analysis of the data from the ASHRAE building. And you'll notice this is the VRF air source, high-end air source solution up here. This is cost versus outdoor temperature. So this is looking at the temperature domain. This is the summer peak over here and the winter peak over here, coldest. And you'll notice the geothermal system runs at a lot lower level. Of course, as we showed you, that battery should be tuned better. And so in reality, it should be running about like that is where it should be running. But still, basically 2 to 1 on the power. So let's overlay what a basic air source heat pump runs as. And that thing is much less efficient than the VRF. And the big deal is that when it gets really cold, down to maybe below like 45 degrees or so, these things will cut into electric strip heat. And that is a much more expensive thing to run. What they call coefficient performance run, just electric strip. We'll never be able to build the grid for that. I mean, you can't build a grid for 4 times the peak when you can build 1 times the peak, you know? So it will never happen. And in reality, even building the grid for the VRF versus the geothermal, it's going to cost an awful lot more. We don't know exactly what this trade-off is because there's installation, which is costing more right now. These batteries are 3 times as much electric versus this, but it's a little more complex. It needs to be modeled to understand it perfectly. So looking at that on here, first of all, the air source heat pump, there's no way we're going to build the grid for that. So it has an infinite time to market as well. And then there's this becomes, including that is not a feasible solution. So those are all not feasible zero carbon grid solutions, zero carbon society solutions. The air source heat pump, the high ends have a coefficient performance of somewhere around 1.8 or so in the winter peaks, maybe 2 in some circumstances, depending on where you are. So they're twice as good as the basic units, the geothermal 4 times as good. And that's why this operational cost curve goes down like that. So looking at the grid, there was a study done in Canada for the Air Conditioning Refrigeration Organization there, and they found that using even those high-end cold climate heat pumps, the grid will cost almost twice as much if you use all air source heat pumps versus all geothermal heat pumps. And going back to this graph now, that creates points like this. So even with that, and we start to understand that even with all these air source heat pumps, it's still going to be very expensive to build that grid. But they're going to have a much higher cost for the grid than if all geothermal heat pumps. What we're going to show is there's another class of batteries in here. Let's just call them other for now. And they are going to produce something better. And we're going to show that they produce an even better cost curve, that we can do better than just conventional geothermal. So we know there's a lot of wind being built. Here's what wind looks like from the energy delivery point of view. It's chaotic. It goes up, it goes down. You have times with massive amounts of wind, time with just moderate amounts of wind. And then if you draw a line here of what you expect to get from your wind, you'll see there's a lot of blank periods where you would get much less, sometimes zero. And you got to watch out because this will coincide with when a snowstorm, you'll get no sun on the PV panels and you'll get no wind. So wind, even during a day, you can see it's chaotic during hours of the day. Switching to solar, you can see solar is chaotic. It's up and down. It's got periods of overcast for days. But we right now have built enough solar that we've got almost all the power we need certain times during the day. And in fact, by 2050, people expect that we're going to build double what we need to get the whole grid to operate. So there's going to be a lot of excess power. There's going to be some periods of really expensive power that you don't want to have to buy it. And there's going to be some periods of really cheap power when you want to be able to use it if you got some way to use it. Well, this stuff has already happened in California. They've already hit zero and beyond for their power production. They're already cutting solar off the grill, what they call curtailment, where they say you can't connect to the grid. That's already happening all the time, even when you would think we still need more renewable energy, but it's not a perfect picture. And right here you can see in these the marginal pricing for power goes way up and way down depending on where you are and the time of day and where the sun's shining. And here in Texas, for example, you can see in up here in the western zone versus the eastern zone, they're through 2009 and 10 even, there were all kinds of periods of negative cost of power from wind. This is a long time ago this started. It's just getting worse and worse. And this you can see from much more recently in 2021, a period of some really low, like cheap, better than free power is in like below zero because they had too much on the grid, and periods of expensive power in different areas. So this whole thing of power fluctuations is a big deal. And that's where these thermal batteries come in. They can store the energy. So if you can get really cheap power, you can use them to store energy. And so that is thermal batteries. First off, there's what's called water tanks, and people have been using these for a while, especially in summer times to store up cold at night and then use it in the afternoon the next day. That's been used for a long time, but people think, oh, well, that's just a way to store cold. It's like, no, it's not. It's a way to store heat and cold with heat pumps. So that's a day-long battery. That water tank is a day-long battery. And to show you how these match up to an analysis we did in these points match up to an analysis we did in Asheville. This is the real load of the generator at Asheville from Duke Energy at the winter peak one year. This is what you'd expect if everyone electrified around here. A lot more people use electric already around here than some other places, especially up north. Take a typical solar curve, map that over it. You might get this kind of a curve from solar during the winter peak, because only during the day are you going to get some savings, not at night at all. With just a water battery tank, you can get this kind of reduction in the peak loading curve, and a very dumb, as you can see, it's not very well done, a very dumb algorithm I just did in a spreadsheet to prove the point, how you can lower the curve back to where it is already now, just with a water battery and a little bit of electric battery. And then how you can get with geothermal get even lower. So how these match up here? Well, there's the water battery. There's the air source heat pump by itself over there. There's the water battery, and there's the geothermal battery. So there's sort of a grid applied real example of what this graph does. So on here now, that other What is that really? What are those things? Well, here's one example. This is a type of battery designed by Dr. Xiaoping Liu at Oak Ridge National Laboratories. That's he's got one of these installed. I made a couple of these installed, but he's got one in particular at University of Illinois, Champaign-Urbana, and it is 2 feet wide and 20 feet long, I believe. HDPE, basically a culvert stuck down in the ground that has a water battery with some phase change inside, and he's got pipes coming out of this several different ways. And basically, this is a 3-in-1 battery. It's a water battery, it's a phase change battery, which will store longer, and it's a ground battery. So it's all 3-in-1, which is very cool. And you could size the different components for what you want. You can create different sizes. You can put in more of them. So that's one way people do this kind of stuff, or will do doing this kind of stuff. And there's another way people use these geothermal systems. They can design fields so that you put all the hot in the middle, for example, and you put all the cold on the outside. And you can design these fields that are gradiated, and you can get better, more efficient recovery of your energy out of them. So there's a lot of variability in this stuff, a lot of engineering that can be done by people who know this, but there's only like 1,500 people who know this stuff at most. So we got to figure out how to get all the engineers on board. So there's those batteries, and they're tuned is the idea of design a tuned battery for your situation, your renewable power fluctuations, your weather fluctuations, your building usage fluctuations. The parameters include, for example, the storage capacity, which ranges from huge to limited, and the bandwidth. So the storage capacity, the water tanks are very limited bandwidth, whereas the ground loops are huge because you got this huge chunk of rock involved with your system. And the bandwidth, in other words, how fast can you get the energy in and out? Very fast for a water tank because you can just pump the water right into your heat pumps. Very low for the ground because you've just got this one little loop in a 20 by 20 big chunk of ground. So these things are all design parameters. And the reality is you've got to figure out how to do that. And here's the example, conclusion of if you took that 3-in-1 battery Dr. Liu did, phase change plus ground plus water, should be able to produce this kind of an optimum point. A properly tuned one should be able to produce this optimum point for heat pump storage, a ground coupled, but also water battery combination. And this produces what we would call the ideal goal cost, the ideal overall maximum, the minimum grid cost to get to zero carbon, and the minimum installation cost to get systems that at least a large percentage of them need to be in this class, in this or this class, or we're not going to be able to build this cost-effective grid. So looking a little bit different at methods. So this tuned thermal batteries and designing how much water battery, how much deep geothermal design factors on the right here. Here's kind of a list of what all's involved. There's the local weather, there's which technologies you're using, phase change, not water, this, that, different grades of heat pumps. What's at your physical site do? For example, at MIT, they have some very poor rock 100 feet down, and you can't really drill it cost effectively, so you just don't do those deep bores there. You do different stuff. They have 100 feet of very saturated clay that you can use. Capacity, what are the capacities you need of each of these different ones to meet the fluctuating power and the fluctuating usage and all that stuff? You see it's a complex model. What's the bandwidth you need to meet the cost models and all that? How do you tune them? How much resilience do you want? In other words, how much reserve capacity do you want for this long periods? Or let's say a piece of equipment fails, pumps fail, whatever, you need to have resilience. What are the installations costs, the operation costs, the grid costs in it? And all of these together controls how fast we are going to be able to decarbonize buildings. So it's understanding how to put this all together is the critical key to rapidly decarbonizing buildings. Clearly, this is a complex model, and there's just no engineer anywhere who's going to sit down and design with this level of complexity involved. So this is why, it requires this level of design to do it. And this is why we are working with the D Lab at MIT and developing an interactive HVAC decarbonization decision support tool. It's a high-level tool to let even lay people in a style of inroads. You should check this out, this inroads style thing. It's a single-page interactive simulator where you put in all these, you select your weather, you load your building data, even if it's just from bills, from monthly bills, or whatever it is you've got. And you model the building, it models the building for you. And then you can project different kinds of combinations of these batteries to get a tuned result. Of course, we're going to add AI as soon as we can to get this right. That's what it requires. It requires developing that. That's what we're out there trying to do. Needless to say, it's complex. This is what's needed. We're not going to get to the zero carbon world quickly and cost effectively without this level of understanding of HVAC. Unless you just go to geothermal heat pumps and you do it right. Unfortunately, a lot of people don't do them right. So the one thing you really want to know is you want to have experts involved in this. None of these are simple. Make sure you have experts involved that have the specific knowledge about what they're doing, especially in geothermal. A lot of engineers have never taken the certified geoexchange designer course. They don't know what they're doing and they screw these things up. It's unfortunate. Thank you.